that's 0, initial volume. Okay. And final volume V. Okay. So that will be, okay, equal to whatever is accumulated inside the reactor. So whatever is accumulated, how much of the number of moles of the reactant J remains unreacted inside the reactor with respect to time. Okay, with respect to time. Okay, so that's the accumulation. So you are feeding the reactor with reactant A, J. So some of them will react, all right, and some of the and some unreacted will flow out of the reactor if it's a continuous reaction. And so those reactant that remains unreacted inside the reactor will be accumulated with respect to time as you feed in more reactant, while some of the unreacted J can leave the reactor. So you can have a measure of how much remains inside, because some reactants J react, but then some remains unreacted at a specific time. So it's an unsteady state operation. So that's the value of J in or unreacted reactant J inside the reactor that accumulates inside the reactor with respect to time as the reaction proceeds. As you feed in the reactor with reactant, and then reactant react inside, and then you form the product, and then but some and when there is what we call continuous flow, the flow of fluid inside the reactor is continuous. So there are some unreacted reactants J that has to leave the reactor and some remains. All right. Any question with that? So this is actually your material balance. Okay. So this discussion, I will not repeat it anymore when we go to our non-isothermal reactor design again. So let me just explain that to you now.
Ma'am,
Yes.
hindi po naka-record yung meeting.
I sorry. Okay. Why is it not recorded?
Thank you, ma'am.
Okay. Oh, let me check. Okay. Okay, let me go back to our meeting. Di ba siya recorded? Mhm. Start video, suspend, active picture screen. Teka, saan ko siya i-remote control? More. Okay. Record to the cloud. Okay. Thank you.
Recording in
So again,
progress.
we'll be continuing our lecture. Okay, very good. All right, can we continue now? So again, that is our material balance. Though sometimes, so you have to look at the big picture of your reactor. Whenever you start your problem solving, you always have to draw your reactor, any given problem that you have. Always represent by a simple diagram, illustration. Okay. Now, sorry. Okay, let me go faster so we will have enough time to finish the problem. Okay. Okay. Now, you know already how we derived therefore the different types of reactor design. All right, for batch, CSTR, and PFR by doing this material balance. So This one, it's like representing now your defining the rate law of your reaction. Okay, rate law. Put your concentration of the reactant in terms of the conversion and plug that into your rate equation. So most of the time you'll be working on this same process in an isothermal reactor design. So in this case, we have your example represents a simple reaction of reactant A going to form your product, say B. So, okay, probably we'll have, all right, so this is J. A plus B going to form C plus D. Okay, so this is the rate law of the reaction for reactant A, for example. Say A is your limiting reactant, and that is directly proportional to concentration of the reactants J. All right, J could be any reactant here. All right, raised to some power n, wherein in this case, if we're not talking of elementary reaction, okay, we're going to define later next meeting non-elementary reaction wherein the rate law is not dependent on the power, which is the coefficient of the reactants A and B. Okay, so this rate could be a non-elementary reaction. Okay, so that's a representation. It elementary reaction is that the rate law is always expressed as the concentration raised to the power, which is equivalent to the coefficient of the reactant A or J. So in this case, this is a typical rate law that is based on non-elementary reaction for this one. Okay. In any case, so we will be discussing that rate law. All right. So, okay. So again, we want to express your concentration C sub j in terms of XA. All right, conversion. So you will have, we have defined already this C sub j, the concentration of reactant A. Now this refers to a gaseous reaction. Usually this is gaseous reaction, okay? Wherein you have to make correction for pressure. This is concentration, analogous to volume in this case, if you want. So volume, for example. So if this is the volume, this is, how much is that? C sub J. So you have to make the pressure factor correction. And then this is actually based on the initial to final. So PO, VO, and then, so this is volume. Okay. So volume inversely proportional to pressure, directly proportional to temperature, and this will be your Z, compressibility factor. Okay, but in this case, this is assumed to be equal to 1 for ideal process. Okay, so rate expression in terms of the conversion. Okay, so you have here. So this is the whole expression for your concentration. All right, so as an example of a C sub j concentration. So if that is your rate law that is dependent on C sub j expressed in terms of the mole fraction, conversion, and the extent of the reaction. Okay. All right. And the extent of the reaction. So this is the whole expression for C sub j, and that will be raised to n. So this is just as an example of your concentration. Okay. Anyway, so So this is the whole rate expression that you're going to plug into your R sub A here. All right. So, all right. So you have that. So the way we arrive at C sub J depends on the particular reaction. Okay. So we will have to study the kinetics of your reaction so we can derive your C sub J. But in this case, this is for a gaseous reaction, wherein C sub JO is the initial. And of course, this is based on the V sub J, which is the coefficient, right? So you know that this is the coefficient in the balance reaction of the reactant. Okay. And epsilon, of course, will be your the sum of the gaseous number of moles of gaseous reactant and product, your epsilon. Okay, so you have that for a gaseous reaction. So that will be the overall design for your reactor. So in this case, the temperature for isothermal reaction is constant. And usually for most reactor, all right, pressure is also constant. So typically this will just be equal to 1 if you have isothermal constant pressure process. So it will just have to be this term. Okay. So the difference between that of the rate law expression for isothermal reactor design is that your X is not dependent on T. All right. But for non-isothermal, again, which I have shown you last time, the X is a function of T. Okay. All right. So next, so we will have to discuss this. So these are your reactor design for isothermal process, isothermal kinetics. All right. I will not review anymore the rate data and the differential method because you're done in doing this, the integral method. Of course, you will be doing the integral method later. You will see a simple representation of graphical integration to show you the numerical techniques of solving the volume in a CSTR, okay, for a non-isothermal process. Okay. So we have the half-life method of determining the rate law or the value of K as well. The initial rates. Okay. Initial rates, this one is the initial rate of the reaction. Okay, method of initial rates. So when the reaction is reversible, okay, the method of initial rates can be used to determine the reaction order and the specific rate constant. Okay, so the assumption is that for a reversible reaction, very little product is initially present. So rate of reverse reaction is negligible. So a series of experiments is carried out. So this is the process of doing the determination of your rate constant and order of the reaction using this method. So review of your differential catalyst bed. So in our catalytic reactor design, okay, usually the discussion is that we have a reactor that's a batch, semi-batch, CST PFR, and then we have another type, which is the pack bed reactor. So the pack bed reactor is always a catalytic reactor. Okay. So pack beds, so the catalysts are packed in the reactor, usually similar to the design of a plug flow reactor. So you have your feed in, feed out, and then the delta W will be the weight of the catalyst, okay, per unit volume of the reactor. Okay, so we're talking now of weight of the catalyst per unit volume of the reactor, and C sub P is the product concentration. Okay, so you have in terms of packed bed reactor, we define the change in the weight of the catalyst in per unit volume of the reactor instead of just simply defining the volume of the reactor. Okay, so this is definitely the rate law for the packed bed reactor is simply this for steady state reaction is this one. Okay, let me just define it first. So let's go through that because you will be looking at this later in your packed bed reactor. So this is the flow rate A, that's it, the balance. And this will be the concentration of AE. Now E represents the equilibrium concentration after the reaction. After, that is at the end of the reaction, the remaining A, which is the concentration of A at equilibrium, the flow rate of A at equilibrium, that is at the end of the reaction. So that whatever is the concentration of A inside the packed bed is the same as the concentration that is leaving the reactor. Okay. And therefore, there's a reaction inside the packed bed. And of course, that depends on how many catalyst, how much catalyst volume, actual volume of catalyst is present. Remember, this bed is porous somewhat. So you have to, this is the whole volume. So the volume of the catalyst, you have to deduct the void space, all right, from the volume of the reactor. Okay, so you have to calculate the actual volume of the catalyst that is present in the packed bed reactor by deducting that pore space, okay, depending on the porosity, all right? So you will see that later then. And this is actually the total weight of the reactor, a catalyst per volume of the reactor. Okay, so that will be your expression for rate law. Okay, for a packed bed reactor. Okay, next, let's go proceed to our next slide. Yes.
Ma'am, question po. Why
Mm.
is it, I want to clarify lang po, why is it that for PFR, the changing variable is volume, but for the catalyst bed, the weight changes as the solution passes through it? Is
Yes,
it?
because what is more relevant here is that the reaction is taking place on the surface of the catalyst. The reaction takes place on the active site of the catalyst that is within the packed bed. Okay, so you have to know that when it's a free space, okay, we just have to consider the total volume of the reactor wherein your reactant is present. Okay, but if it's a packed bed, of course, your catalyst is responsible for the faster reaction. So your catalyst is porous. So your reactant has to penetrate that catalyst. Inside the catalyst pores, it will be adsorbed first. So the reactor, actually, the reaction is happening on the surface of the catalyst. So that's why you have to know the weight of the catalyst per unit volume of the reactor. So this is the volume of the reactor. How much is the catalyst that is present there? All right. So definitely it's a packed bed reactor. So you have to know the weight of the catalyst, all right, per unit volume where the reaction is taking place. Okay, that's why it's not the volume. This is actually weight per volume naman ng reactor. Weight catalyst per volume reactor. Okay, you will see more of this when we discuss the catalytic reaction. All right. So it's the variable, of course, is also the volume that varies, and then also the weight of the catalyst that varies with the volume per unit volume of the reactor. Okay. So it's more on the how much of the packed bed you need for the reaction to proceed so that you can have this final conversion of CaO to CaE. So that is always a question. All right. So later you will see more because the reaction is not taking place on the free space of the reactor volume, but on the surface of the catalyst. So it's the weight of the catalyst per unit volume of the catalyst. That's how we design it. So the pack bed. How much catalyst are you going to put in the reactor? So that's also another question for the reactor design. So there could be that question again, because the reaction rate law has to be dependent on the catalyst per active site of the catalyst. Okay. Is there any other question? So that's the difference between a plug flow and the pack bed. So we're more concerned, of course, with the volume for a plug flow, because your reactant is supposed to occupy the whole volume of your reactor if it's gaseous. And for the gaseous reactant that's flowing through a pack bed, when we have a catalyst, the catalyst serves as the reaction, as the site of the reaction. The reaction occurs only on the active site of the catalyst. That is our assumption. Because for some reaction, it's not easy for them to, it's not for catalytic reaction, for say mostly petroleum chemical cracking of hydrocarbon, long chain hydrocarbon compound in petroleum processing. So usually we have a lot of catalysts to hasten, to improve the rate of reaction. So that's always the case. Okay. All right, next. So where is my pen? Okay, next slide. Again, so this is our main class discussion. Just to run through the basic rate expression and also the design equation for a multiple reaction. So that part is just a review, and this is actually our discussion. Okay. So we'll be discussing more of that pack bed then for when we discuss catalytic reactors. Okay. Now let me go over the summary of the rate equations and also the reactor design for multiple reactions that could be a parallel and series. And then we could discuss more complex reactions. So classification, again, so you're familiar with the parallel or competing reaction. Usually K1 represents the direction of the desired, and then the AK2, the undesired product. Okay? Alin ba yung desired dito? Okay, ito daw yung desired in this case, and this is the undesired product reaction. So the desired product is this one, the first reaction, and then this product, there will be a side reaction to form the undesired product. Okay, so this is our desired product, forming 2 moles of each CO2 and water. And then independent reaction. So we have, so this is a type of parallel or competing reactions. Okay. Series reaction and then independent reaction. And so most example is that if you're going to work in a crude oil cracking, because you have a very long chain hydrocarbon compounds that you want to reduce to say C12 or C6. All right, so that is usually done in fluidized bed reactor. Okay, and this is crude oil cracking, independent reaction. And then you have complex reaction as well. So when you say complex, it's more like you have several reactants forming several product, and then your previous reactant and the new product will interact to form a new product E. So that's complex reaction. Okay. So writing the rate expression, rate law, recall, you still recall how to write the rate law. So again, KD will be rate constant, dependent on the concentration of A and B. Now, alpha 1 and beta 1 refers to the order of the reaction. So we will not say that the reaction power with respect to A and B are just equal to 1. Okay, that's not correct because we're talking of non-elementary reactions here. We're in the power of your of your reactant A and B concentration are not dependent on the coefficient. Okay, so those are non-elementary reactions. So you have to know the order of your reaction. Okay, with respect to each reactant. So for the andesite, this is your reactant CA and B again for the second reaction, the andesite one. All right, so again, the K is a function of temperature, and therefore Ra represents the total rate, net rate. Rate of disappearance of A will have to be dependent on two rates that's competing, right? We are saying that these two are competing with respect to A. And so the rate for the formation of D plus the rate for the formation of U will be the net rate for reactant A. And so you have the, of course, defining your K as a function of temperature T of the reaction. So whatever is the T of the reaction, you can express your K as a function of the temperature with respect to the use of the Arrhenius theorem, K of T. All right. So this one, just express Ku in terms of the Arrhenius constant, AU, and then the activation energy, and then R and T, temperature of the reaction. T again here is constant temperature of the reaction. Okay, and defining the instantaneous rate selectivity. So you have the ratio of your rate of formation of D to the rate of formation of the andesite product. All right. So substituting the expression of Ra and Ru, so you have this. Okay. So that is your instantaneous rate selectivity. Okay, so you can have other expression for that. If you want to define in terms of K or you want to define in terms of the Arrhenius constant. So you can group them so that you can arrange the powers of Ca and B product, and then you have the quotient. So quotient is A1 alpha, alpha minus 1. So beta 1 minus beta 2. Okay, so that's a simplified form. All right, so goal is you maximize that ratio. When you maximize this ratio, it says that you are going to favor the formation of more desired product. You know how to maximize this expression. So that's part of the simulation process that has to be done if you're going to deal with this. So what reactor conditions and configuration maximizes the selectivity? Okay, so you have to make sure that you can, are we going to control T? You have to choose a temperature at which it gives you the maximum value of D. Okay, so you can substitute any temperature here and compare the value of SD over U. Okay, or you can vary your CA, you can vary your CB. All right, so at what value of A, B, concentration and temperature are you going to have the maximum ratio? Because the maximum ratio gives you the higher value of the desired reaction. So in order to do the simulation process, you start with temperature. Okay, it affects the value of K. So that's why you have to vary T and observe what happens. All right. So of course, there are two assumptions. If the activation energy will be greater than EU for the DNA, and case B have D less than U activation energy. So that will be your process. So that way you can actually uh, specify. So for case one, you have to use higher temperature to favor desired product formation. For case two, just a summary, use lower temperature to favor the desired product formation, not so low that the reaction rate is so tiny. So in this way, the best way to see this explanation is to do your graphical S versus T. Okay, you assume several T, increasing T for case 1 and decreasing T for case 2. So you can see how the ratio of rate of D over U will vary. Okay, so that's just one way. Now, let me go faster. Okay, so what reactor temperature maximizes the selectivity? So in this case, this is an example wherein you have deluge, I mean, 20 and 10 for the value of the activation energy at 25 and 100 as the temperature 125. So you have both. So we'll just go with the final answer at 25 for case A and at 100 for case A. All right. So we get to define KDU, all right? So obtain that KDU for case A. So our value therefore is that the conclusion is that the ratio is greater at 100, higher temperature to favor desired product formation. Okay, because what happened is that this quantity here is 4.6 to the negative 8 is much smaller as compared to 1.4 times 10 to the negative 6 is much bigger for the same concentration and the same activation energy ratio, right? Because this two will just cancel anyway. So what's more important is this one, since you're talking of the same concentration for both type of reaction at 25 and 100, because you will just vary the temperature. All right. And so that will be your answer. So at 100, definitely. Okay. So you can see as an example, this is what you have done in your kinetics 1, correct? This is just a review actually of what you have done in a series of, I mean, in your multiple reaction discussion in kinetics 1. So maximizing the for parallel reaction concentration. Okay, now what reactor condition and configuration maximizes the selectivity? Now evaluate concentration this time. Let me do it quick. Concentration. Now, of course, the concentration has to be both dependent on the order. But order of the reaction will not change for each reactant. For case A and case B, we just have to vary concentration. For case A, we use higher concentration. For CA, we use smaller concentration. So this is somewhat your simulation process for the multiple reactions. So questions of our class?
Nag-
Okay, very good. So The order of the reaction, of course, will remain the same when we are comparing. We will not vary those order of the reaction, but only the concentration of our reactants and A and B, right? So which of these two? Because the objective is we want to maximize the formation of your desired product. And so though this is actually, maybe you can include similar case when you want to come up with your own, what do you call that, reactor design simulation, but non-isothermal, okay? So this might be useful. Okay, so let's substitute the values. And this one is for PFR or pack bed, because the design for a pack bed and for a CSTR, sorry, PFR and pack bed are the same. For batch is different, and for CSTR it will be different. And so this will be your answer to a summary, no, of the chapter. How do concentration requirements play into reactor selection? So in that case, we have for the first one, okay, for PFR, the concentration is high at the inlet, which is correct because at the inlet, the reactor the reactor, the reactant flows, and so the reaction will start. So the maximum concentration of the reactant will start at the entrance, okay? All right, at the entrance, right? Wherein the conversion is yet zero, is still zero. All right. And so progressively drops to the outlet concentration. Okay. So concentration for a CSTR is always at its lowest value at the outlet. Okay, because whatever is leaving is already the end of the reaction. Usually that is always the after the reaction has been done. So the minimum amount, okay, will be present at the outlet for a CSTR. Okay, so for a batch, concentration is high, of course, initially at the start of the reaction, progressively drops with increasing time, okay? And for semi-batch, concentration of one reactant is shown is high at T0 at initial and progressively drops with increasing time, whereas concentration of B can be kept low at all times, okay? All right, so that is the case for the four cases. So we have, so given that condition for each type of reactor, all right, so this will be the effect, all right, for each type of reactor on selectivity. So high concentration definitely of A favors desired product formation, all right? So KD, as long as KD is your desired reaction, KD usually is higher than KU. So the higher CA, it favors the desired formation in general. If alpha 1, all right, the power of the order of A is greater than 2, okay? So if the other way is vice versa, no? Alpha 1 is less than the 2, the high CA favors the undesired product. So you have to keep the concentration of CA low. So that will be in general, no? In general for alpha 1 and 2. Now, if we're talking of batch reactors, okay, all right, so when we're talking of beta, the concentration of B reactant, second reactant, wherein beta 1 is greater than beta 2, all right? So beta 1 will be for the forward greater than the beta 2. So high CB, therefore, again, favors the desired product formation. So when for a batch reactor, hold on, the CA and CB are low, okay? When they are low, okay, for alpha 1 greater than alpha 2 and for beta 1 greater than beta 2, okay, the order. So both cases favors the forward, right? The higher the CA, the higher the CB favors the formation, desired formation. So when CA and CB are low, end time or position, all reaction will be slow, all right? All reaction will be slow. And so that will be for the batch, all right? So for high product, for high P for pressure, sorry. High pressure for gaseous phase reaction. For high pressure, okay, PFR or packed bed reactor. Okay, do not add inert gas or because that will dilute your reactant. All right, so that is the assumption here. For this case, for packed bed or plug flow, high pressure for gas phase reaction. The thing is you do not have to add an inert gas because it dilutes your reactant. Because we want for beta 1, beta 2 greater than that. So for this case 1, okay, for this case 1, I think, okay. So this is part of the decision making when you're trying to design your reactor. So this is very important. For high pressure, you don't need to dilute your reactant by adding inert gas. Okay. All right. So that's it. So let's go to the next case. So there should be a lot of cases. So this is how you're going to interpret the result. I mean, how you're going to design your reactor. So this is actually a very nice lecture of Dr. Kraft. And this is Dr. Kraft lecture from Illinois. So I would be uh, happy to share this with you, class. Are you following me, class, in this discussion?
Yes, ma'am.
Yes.
Okay. So this is actually when you try to design, di ba, for a multiple reactor. All right. So maybe you can use this later when you are going to prepare your simulation project. That's why. Anyway, so decision making when you have again this table. Okay, again, this table now we have the second case wherein the beta is less. Beta 1 is less. This one, ang power ni beta sa first reaction is less than the power dito sa second. So, ibig sabihin, mas mabilis mag-form si undesired. Mas higher the B, mas maraming mafo-form na undesired with respect to B concentration. Dito naman, mas malaking A concentration, mas marami pa ring desired. So, meaning keeping CA high, keeping B low. So, that's how we are going to use that. So, in this case, for a CSTR and PFR, sorry, for a CSTR and PFR, so, hold on. Okay, this one. For a CSTR, this is actually our objective. High CA, low B. And then for a PFR, okay, dilute with high recycle, no? This one, the PFR. Dilute feed with inerts that are easily separated from product, okay? We have to dilute feed for inerts. So high CV favors undesired product formation. So keep CB low. Okay, so that's why. Anyway, so this one, uh, so for this case, no, low pressure if gas phase. Okay, so in the case of PFR, we have to use low pressure if the system is gas phase. If liquid phase kasi, no problem. Pressure is always maintained at 1 atmosphere room atmospheric pressure We don't want the CSTR to be at a higher pressure. We don't want that. So usually we usually have the CSTR at normal pressure, operating pressure. For gaseous, of course, you have to keep the pressure low for packed bed or for plug flow reactor with high recycle, meaning to say all unreacted reactant will have to go back here. You have to recycle. That's the suggestion. So this one will be less again. The desired is B1 is less than B2, and in this case, you have alpha 1 greater than alpha 2. So for this one, we have, okay, alpha 1 is greater. So again, CA must be higher. Alpha 1 is less, sorry, and B2 is less. Sorry, parang nagkamali ako kanina. Alpha 1 is less, so CA must be kept low. B1 is less, so B must be kept low. Pareho palang low, sorry. So both C and B must be low in concentration. A and B must be low in concentration. So therefore, you have to dilute the feed with inerts, okay, to keep the concentration of A and B as low as possible. So you have to recycle so that you can consume all A and B that you diluted. Okay, so that will be for both CSTR and plug flow. Sorry for that. I got confused with the greater and equal sign. Yes. Now for the third case we have here, that's why I'm confused with my statement earlier. So this one is A1 greater. Again, this is keeping CA high and keeping B low. So in this case, we have for pack bed or PFR with side stream feeding, to keep the low CB because we want the CB to be low. So your B has to be fed, all right, one at a time, slowly throughout the length of the reactor. So that will be the technique to keep the B concentration low enough. So there is what we call the side stream feeding. So really, some reactor design are have side stream feeding because of this case to prevent the reaction formation of the undesired product. So that is the idea, especially for most reactions that are multiple. Okay, this is just competing reaction. For semi-batch, okay, reactor, okay, you have slowly feed B to large amount of A because we want to keep A large. So in a semi-batch, you have to keep A high and slowly feeding B. Okay, slow lang, slowly, little by little. Parang you're mixing sugar when you're baking, no? Add little by little, one at a time. Okay. So it's like cooking. So when you have a chemical reaction, it's like you're making your baking or you're cooking. So same as that. So CSTR in series. Okay. So you can design a reactor wherein you have a series CSTR. So B is consumed before leaving CSTRN. So these are the consideration when you have the design of the multiple reactor. Where is my slide? Next. Asan yung fourth slide? Okay. Ayun. All right. Now, keeping when both B1 greater, this time yung B naman, higher concentration of B favors product and high concentration of A forms more undesired. So, baliktad naman. So, yun. Baliktad din yung case from this case to this case. So, the same, but same approach. Okay, this time, B naman will be the one in higher concentration and A will be the one in lower concentration. Same for semi-batch and for CSTR in series. Okay, So that will be part of the design consideration. So different types of selectivity and so on. All right. Now I would want to discuss with you one problem, and so it's already 5:30. I will have to rush my discussion here. So I want everybody to read the rest of the slide, since this is just a review. Okay. Instantaneous yield, overall yield, time is a key factor here, space time. All right, series reaction. So for the series reaction, we will have to be doing this same setup. Okay. And so one example that I have here is a series reaction. So I'll try to do the mirroring so I can control my pen. So let's mirror the presentation na lang. Let me mirror the presentation class very quick. Okay, then. So let me give you one reaction, and this is a series reaction. Okay. A series reaction. So in 30 minutes, we should be able to define this. And the activity that you will be doing until next meeting is that you will try to solve this reaction or try to do the calculation. You will just be doing the calculation and practice using your ODE 45 in solving the three differential equation. Okay. So let me. So this is already mirroring my iPad. Okay. And so this is your problem. So this is our problem. Everybody can see this problem, right?
Yes, ma'am.
Yes. Okay. Now, let me have my color. So you can find this in Fagler naman. So there are three problems, but we can only afford one. So you can study the rest of the other two problems for this multiple reaction. So this is our two reactions. You have the M-silane is produced by the hydroalkynation of mesitylene. Um, okay, mesitylene. Ito pala yun. Producing M-silene. M-silene. Ay, mali. Okay. So this is M-silene or just X. All right. So, and this is your methane part of and this is hydrogen. Okay. So this will be our symbol for the reaction. So this product M-silene, which is symbolized as X, will have to react further with hydrogen, not the same reactant, and that will form your toluene T and another methane. Okay. So second reaction is the undesirable one. So this is your undesired reaction. Here's some information. Okay, sorry, I pressed my. Paano ba to? Okay, ayan na. So the second reaction is undesirable. The N-silene sells for a higher price than the toluene. So thus we see that there is a significant incentive to maximize the production of M-silene. So we want to maximize this product. Okay. And so the hydroalkylation of the mesitylene is to be carried out isothermally. So this is isothermal at 1.5 Rankine and 35 atmosphere packed bed reactor. So the pressure is very high. It's 35 and it's a packed bed reactor in which the feed is 66.7% mole of hydrogen and 33% mole of what's this, mesitylene. Okay, so just remember this: 66 hydrogen, 33.3 mesitylene. So the volumetric feed rate is given at the V sub O volumetric feed rate at 476, okay, cubic feet per hour. And the reactor volume is given as well. It's around 238 cubic feet. Okay, and so the rate laws of the reactions are known. All right, so we have, so this is the feed composition, and this is the flow rate, and this is the volume of the reactor. Take note of that quantity. And the rate of the reactions are already given. So these are already given. And therefore, the reaction taking place at 1.5, the K1 at 1.5, all right, are given, K1 and K2 for the two reactions. So this will be your desired and this will be the undesired. All right, so the bulk density of the catalyst has been included in the specific reaction rate. So of course, the catalyst, again, this is a packed bed reactor. You always have to consider this is density of the bed. Density of the bed means it's the mass of catalyst per volume. The bulk density of the catalyst is included in the specific mass of catalyst per volume catalyst. Okay, so that is K1. So this is included already in K1, accounted already. So plot the concentration of hydrogen. So you just want to have, therefore, a plot of the concentration of hydrogen, mesitylene, silene, as a function of the tau. Okay, so those three: hydrogen, mesitylene, silene as a function of time. Okay, so you just have to know the plots, plot them. So in that way, you have to know the changes in the concentration of hydrogen, concentration of mesitylene, and M-silene with respect to tau. All right, so that is our objective, set concentration. So for solving the problem, therefore, of course, you know how to do the basic stoichiometry and determining the rate law. Okay, and so we can finish this on time. So reaction one will be this. So solving this, you have to assign, okay, reaction one and reaction two. Start with your reaction, the desired reaction, and then the undesired. Mole balance. So how do you do the mole balance? This is rate. Usually when you say rate, rate is the Ca over dt. But of course, the derivative of Ca is number of moles of A with respect to volume and therefore with respect to time. And so usually when we're discussing flow processes, we usually define flow rate, molar flow rate. So that is rearranging that, therefore, molar flow rate, I will have to take in Na over T. So that defines my dFH in this case over the dV. All right. So it's like dNA over dV over dt. All right. So you get to define your, sorry, dNA over dt. dNA over dt. So that is simply dNA over dt with respect to dV. All right, so you have that. So you can define your rate in terms of the derivative of the flow rate with respect to volume. Follow, class? Okay, so you
Yep.
can see. So how you define your rate expression in terms of the flow rate. Okay. And so same for both, for all the component. So you have how many reactants here? Hydrogen, and then two products, toluene and methane. Okay? So lahat yan. So it's like the flow rate, changing flow rate. So it's when you have this differential equation, you have the changing flow rate of hydrogen is always dependent on the reaction rate and the changing volume. Whatever is that volume that is changing, that is happening within the reactor volume. So something like within that portion of the reactor. So this is your delta V. And so the rate of reaction for each section of the reaction. So that changes, therefore, the flow rate of H as the reaction proceeds from one part of the volume to the next part of the volume. Especially for the plug flow reactor, this is very common. Are we talking of pack bed? So this is pack bed anyway. So we're talking of that. So you can see how we can express the flow of your reactant as it passes through the first part of the reactor, second part, third part. The conversion is x1, x2, x3. All right. So that is a pack bed. And this is the final flow, FH. It will be leaving at FH, the final, and this is the initial, FH sub O. All right. So you're looking at that change, the differential form. Okay. So the rate law and net rates are given. So these are always given. Now I'm looking at my, okay. So rate law means you have to define the rate law with respect to M. Let me show you the, can I show two screens so that you can see the reactor and the you can see the mirror as well as the problem, which is here. So you'll be looking at the mirror and the problem, but then let me reduce the size of this so you can see the problem and the mirror as well. So I can define this. Can you see the slide clearly, class, even if it's not that big on your screen? Okay, let me just define this rate reaction 1, which is defined here. So let's take a look at the reaction, this reaction here, okay? All right, so when I define the reaction rate, so I'm looking at my screen pala. Favorite color. So this is reaction 1 for the M, methylene. Ano yan? Mesitylene. Forgot that. Mesitylene, okay? The reactant. Okay. For reaction 1, that is for the desired reaction, and that is K1. Of course, rate law, the power of the order of H, hydrogen is 1/2, and for the reactant M, it's 1. And so for rate 2, reaction 2, I am defining here the rate for toluene for reaction 2. And you can see that the toluene reaction here is, okay, let me, so this is toluene, and I'm defining here rate of toluene in reaction 2. In reaction 1, I'm defining the rate of reactant, M, and reaction 2, I'm the undesired product, which is toluene. Okay, that's K2CH raised to 1 half CX. That's dependent on reactants X and H. And so the relative rates, meaning to say, will be the rate of hydrogen in reaction 1. Okay, negative means because it's reactant. Rate is decreasing, concentration is decreasing with time. So multiply by negative, that makes the rate low or rate of reaction positive, an absolute quantity, not a negative quantity. All right. And so relative rates, that means the rate of hydrogen in reaction 1 is the same as the rate of your, what do you call that, mesitylene, the reactant. And then that is the same as the rate of the product methane in reaction 1, and same rate as the rate of the silene, M-silene in reaction 1. All rates are equal. Same for reaction 2. Rate of toluene, rate of methane, and the rate of hydrogen for reaction 2, and rate of the silene must be equal. So relatively, all the rates are equal. The mole ratio is 1:1:1. Okay. Therefore, if that is the case, the net rate of the reaction, okay? So we'll be discussing net rate again when we talk of non-elementary reaction class. So take note, non-elementary reaction, we will discuss later, maybe next meeting. Still have time. Okay. Anyway, so RM, you know how to get the net rate, right? Just give you one example. This one is just simple. So RM, let me talk of, or you're looking at this, plus RM, the rate of reaction of the reactant, and that will be the rate of the reaction of M in reaction 1. Okay, that's why it's 1. And that will be K1. Again, this is the rate expression for the rate of formation of reaction of the reactant in reaction 1, the desired product. Okay, so for the rate of hydrogen, hydrogen is present in the 2 reaction 1 and 2. So for both, hydrogen is being consumed. So net rate will be the sum of rate for reaction 1 and reaction 2 for hydrogen. And in this case, since the rate of reaction of hydrogen in reaction 2, which is this, is the same as the rate of the undesired product, toluene. All right. So you can also say that the rate of hydrogen net will just be the sum of the rate of hydrogen in the first reaction. And that will be this reaction, the reaction here at reaction 1 for hydrogen. And also, instead of the rate of hydrogen consumption in reaction 2, and you just have to express that rate of hydrogen in reaction 2, same as the rate of reaction of the undesired product, because usually the rate of the undesired product formation is usually given. And so if that is formation, that is positive, so you just take the negative of that rate. of the reaction of the product, negative of this. Okay, because if hydrogen is consumption, this toluene is formation. So you have to take the negative of that. Negative, negative, positive. Okay. Anyway, so that the rate of reaction of hydrogen will be both negative is its consumption. So that is this expression. Question here, class? So that's how you take the net rate. Same for Rx and same for RME. And this is R toluene, or the R of toluene in the second reaction, because toluene is formed in the second reaction. So you have to label that as R2T. All right. Anyway, so these are the expression for the rate of the reaction. Now we go to stoichiometry. Our objective again is finding the concentration of your reactants remaining and product that has been formed, this concentration. So how are we going to get that? So first we start with the rate expression. All right, defining the flow rate changes, the rate expression, the rate law. We know that with respect to the flow rate of the feed in and out, flow rate of reactant in, flow rate of reactant, unreacted, and product out, okay, that is rate. And this rate is defined in terms of this net rate, all right? We're talking of this net rate. So we have now expressed the rate in terms of concentration that we want. But of course, we need to know the initial, okay, values of the concentration. Okay, stoichiometry, volumetric flow rate is given. So since temperature is constant, pressure is constant. So we just have to deal with this later. So flow rate is constant, steady state operation. Flow rate in and out must be constant. So that will be here. So that the flow rate in the reactor, since this is packed bed anyway, so the flow rate in and flow rate out will be constant for a steady state operation. And all T and P constant. All right. So the flow rates will be defined in terms of the volumetric flow rate, which is the unit of that is the volume, say cubic meter per, unit time, second. And then the concentration will be terms of mole per cubic volume. So unit of volume will cancel. And so that is, sorry, this is FH. And so it will give you somewhat a measure of the flow rate, molar flow rate, mole per unit time. Okay, so that will be our unit, mole per unit time, mole per second, for example. So that will be your volume, metric flow rate times the concentration of each. So that's it. Okay, actually, this is actually your review of your stoic and mole balance. Okay, so you do the same for your reactant and product. Okay, so let me go through that. So everybody knows how to do this, right? No problem with that. So I only have 8 minutes to do this. Now, this is the second part. So defining now our tau, your residence time. Volume is known, volumetric flow rate is known. So we can calculate this tau. All right. So therefore, we have an expression coming from here, d tau. When we define B, which is a constant, and we have defined tau in terms of V sub O. V sub O is simply f of t divided by, multiplied by, therefore, CMO minus CM, for example, minus CX. Okay. So this is an expression for V sub O, correct? So that is an expression for V over V sub O. This is an expression for tau. All right. So this is the tau. So if I will have to take the derivative of say in this case, okay, let me just give you a specific equation to get the derivative. CH K1 K2. All right, CH K1 K2. So you try to combining the and substituting in terms of, if we know CMCH, okay. So get an expression for d tau, okay, and the V sub O expressed in terms of this, okay, K1, K2, CH, the flow rates, which is this. Substitute the flow rates and get DCH over D tau. Okay. Combine this and this tau expression. All right, I forgot to define that. So tau. And so defining dv over d tau is v over v sub o. So you now know how to get tau. dch over d tau, d time is rate, okay? So dch over d tau is simply almost equal to time, okay? So this is the same expression as that, dch over d tau, okay? So that will be your expression. So dCA over d tau, get the derivative of CA over d tau. So you get this. So K1, so in this case, our dCH over d tau is K1, CH, K to the 1 and 2. So that is the rate of H. Okay, see the rate of H. That is just dCA over d tau. R sub H, net rate, is negative K1 CH to the 1 half CM minus K2 CH to the 1 half CX, okay? So that is simply your dCH over d tau is simply your R sub H and so on. Okay, so you have this expression. This is the differential equation that you have to solve. You know tau. So when you try to transport tau here, this is d tau. Okay, and put it so when you integrate tau, that is from 0 to tau, which is known already. Check. So you know your delta tau, which is tau as measured here, it's 0.5. So in your differential equation, ODE 45, that's 0.5. So you have to divide that 0.5 into, say, 10 interval. So you know your H, 0.05 H step. And then you have CH. The integral of that CH, of course, remember your ODE 45 in solving that three equations here, three unknowns. Therefore, your DH naman, integral of DCH, concentration. So you have CHO and CH, which is the known. So CH minus CHO is equal to this f of x natin, multiply by your delta tau. Okay, so recall ODE 45, CAI plus 1 is CAI plus the change, which is f of x delta tau. But of course, based on ODE 45, you have to define this in terms of your K1, K2, K3, K4, so that you can predict, okay, the new concentration for every age interval, all right, for every age. So you can have that as 100 if you want, or gusto nyo 20 lang, pwede naman. 10, okay na. So you can do the iteration several times until you reach ang age natin, 0.05 to 0.5. So this is your time span in your ODE 45. And this is your CAO initial, which is calculated here as, what is that CAO? Kung ano yung CA natin. Ayan, kinalculate naman lahat ng initial concentration. And then plug these values of CA na initial, check, given, time span, check, ODE 45, okay, time span, given, CAO, time span. And then ano yung output natin? CM lang, concentration. And yan. Okay, so that will be the content of your ODE 45. Try to solve the concentration given this three differential equation, initial condition, and tau. Based on that, MATLAB programming, hindi Polymath na MATLAB, ODE 45. Ito yan, ODE report, Rinjikuta, fourth order. Kaya 45 yan eh. Okay, yung pang 45 na ODE toolbox. Okay, so use this to find your graph. Solve this graph. Do that next meeting class. You submit as a group. If you can't do it next meeting, within the week or until next week, fine. All right, but you have to learn how to do this. This is your problem set 1.1. Okay? As a practice, you have to learn how to do ODE 45 as a practice. So bring out that graph. Produce this graph. Okay, class? That's all for today's lecture. For the rest, you can, CSTR kasi madali lang to eh. Direct calculation ng CSTR. You don't need any differential equation here. You just use EPSOL for CSTR. And for the last one, mas madali. Okay, you can just do one problem exercise for now. All right. So,
Ma'am?
do you have, yes, question?
So problem set 1.1 is the problem discussed earlier. Then we can submit
Yeah.
at the end of the week.
Yes, you can, or early next week, possible. Just learn how to do it in the solution. No? The problem is already solved. You just have to learn how to do MATLAB solution using ODE 45. Practice lang kayo. Do the graphing, do the use ODE 45. And so you know already what is happening in the cycle, in the iteration, right? So I showed you already that differential equation. And you don't really have to write the program here, no? Kasi mahaba yan. And then tatlo yan, nagagamitan niya. So just do it that way. Okay. Kung gusto niyo, one at a time. But then again, sunod-sunod naman eh. All right? So try to know how you will be using, how to solve all these three equations here. This is reaction 1, reaction 2, reaction 1, reaction 1, reaction 2. Okay, take note. And then you're just trying to solve for CH in reaction 2 or reaction 1, CH in reaction 2, reaction 1. Okay? Try to figure out how your Practice muna kayo mag-solve nitong tatlong differential equation na yun. Okay, let's see. And maybe, can you do that next meeting or next week na? Para I'll give you time to study. Then next week na natin i-discuss yung output niya. No?
Okay po, ma'am.
So, yan yung PS 1.1 natin. Practice. Continue learning your ODE 45 using this equation here. Actually, meron yan. Try nyo kung may ma-download kayo na this same solution using MATLAB sa website ni Fagler. Yun na lang aralin nyo din if you want. Anyway, we just need to learn how to, you learn how to do that on your own muna. Sige, go. So I'll be meeting you next meeting, Thursday, and our topic will be non-elementary reactions. Okay, and then pseudo steady state hypothesis application, finding the net rate of the reaction, and writing the rate law for non-elementary reactions. Okay, so mechanism of the reaction, maybe a little bit exercise on how to write the mechanism, actually predict the mechanism of the reaction and writing the rate law. That will be all, class, for today.